Water is a key resource for humankind. One way to improve its sustainable management is the use of several types of sensors that can be adopted to monitor different parameters of this fluid. We can group them into three classes. The first one includes sensors to monitor water quantity, such as pressure and flow rate. The second one includes sensors to monitor water quality by means of chemophysical parameters such as temperature, ionic conductivity, that is salinity, pH, and concentration of specific ions or molecules or even biological entities. And finally, sensors to monitor the infrastructure which transports water, typically pipelines made of metal or plastic that can be affected by fouling, corrosion, and leakage. Analytical instrumentation can be operated in laboratory to analyze water samples, periodically collected by human operators, also running the analysis, or can be installed online in the distribution network for continuous, autonomous, real-time measurement. Clearly, online monitoring provides evident advantages in terms of automation and temporal resolution. If several sensing nodes are installed in the distribution network, the spatial resolution in monitoring is also greatly improved. A dense spatio-temporal granularity of data allows early detection of faults, fast response to critical anomalies, and predictive maintenance. Sensors are thus combined with modeling, needed for instance to study the locations and the parameters to be monitored, and the optimal ways to merge heterogeneous information. They are combined with decision support systems, enabled by analytics on the acquired data. Sensors could be classified according to several criteria: the sensing principle, the metrological performance, the cost, bulkiness, output type, and so on. An important classification from the practical point of view is the installation type. Most sensors require direct contact with the water and thus need to cross the pipe wall by means of some drill opening. Instead, some sensors are contactless and can be applied externally on the pipe with evident advantages in terms of robustness. Sensors requiring contact with the water are all electrochemical sensors: pH, chlorine, dissolved oxygen, optical ones such as turbidimeters, pressure, temperature, and several types of flow rate sensors: turbines, Venturi type, electromagnetic ones. Instead, contactless sensors are, for instance, conductivity and ultrasound flow rate sensors that can be clamped on rigid pipes. They leverage the dependence on the fluid speed of the time of flight of two counter-propagating ultrasonic waves. Since water leakage is a major problem, in Italy, for instance, an average of 40% of the drinking water is lost in the network, several sensitive technologies have been developed to detect leaks, spanning from hydrophones, noise correlators, and accelerometers to optical fibers and conductors for time domain reflectometry and impedance detection. The current trend is to adopt Internet of Things technologies for environmental monitoring of urban areas, smart cities where traffic, waste management, air quality, and noise pollution are measured, as well as rural ones for precision agriculture and preservation of natural resources. Water represents a perfect case for the application of these pervasive technologies. All these sensors can be embedded in compact electronic units installed in critical sections of the water distribution pipeline. They communicate by means of radio channels, thus forming a wireless sensors network. The most common network topology is locally a star. Individual sensing nodes communicate through low power, low data rate, long-range radio protocols with a central gateway. The average distance between them can be up to several kilometers. The gateway is then permanently connected to the cloud, where data can be collected, stored, processed and analyzed, shared and visualized by the user from any fixed or mobile terminal. End users can be utilities companies, managing water distribution networks, as well as individual citizens. The technological pillars supporting this trend, which is evolving from being emerging to be consolidated, are the following: miniaturization of electronics and sensors, concurrent increase of the computational power of microsystems, development of ever-improving telecommunication infrastructures, development of low-power and energy harvesting solutions, flourishing of machine learning techniques. Machine learning allows to process large amounts of data produced by deeply sensorized environments, and thus to automatically and rapidly extract information useful to control systems and for decision makers. Despite being a very promising vision, a pervasive, widespread diffusion of these sensing nodes has to face two major challenges: power dissipation and cost. Thanks to the constant reduction of the power requirements for commercial electronic components, and thanks to the abundance of energy sources along water distribution networks, energetic autonomy is easily achievable by the sensing node. The most interesting sources of energy in the environment for this context are photovoltaic, vibrational, geothermal, and kinetic energy of the water flow. The cost of each individual unit is critical, since hundreds to thousands of them should be installed to properly map a real water transport network. Once the ongoing crisis of the semiconductors industry will be over, the cost of electronic components can be significantly reduced when mass production volumes are achieved, especially when microelectronic integrated solutions are leveraged. The remaining dominant cost terms will be R&D, the calibration needed for some type of sensor but avoidable if the target accuracy requirements are relaxed thanks to a multiplicity of sensing spots, and the installation cost. Retrofitting techniques allow to install sensors, both contactless and intrusive ones, on already installed pipelines in a minimally invasive ways. The gains in terms of reduced risk, early detection, and predictive maintenance compensate the investment in such technologies.